Hi everyone, my name is Mahdi. I'm a second-year PhD student at Penn State. Today I want to present a project titled Decarbonizing Concrete by using Biochar as lightweight aggregate. This project is advised by Dr. Farshad Rajabipur, and it's done at Penn State, Department of Civil and Environmental Engineering, and is funded by CM. To start with, let's get familiar with what biochar is at the first place. So biochar is a carbon-rich material which is produced when a biomass, also known as feedstock, undergoes a thermochemical conversion, which we call pyrolysis. And what we get out of this process is called biochar. So we could use a different feedstock or biomasses to produce biochar. The most important ones are probably wheat straw and wood waste. And also the pyrolysis could be done at different temperature, heating temperature rates and pressure levels. So depending on the feedstock type and also the pyrolysis parameters, what the final properties of biochar would of course be different. So why do we want to use biochar in cementitious mixtures? So we all know that concrete, and more specifically cement, is responsible for a huge amount of CO2 emissions globally. And we as concrete researchers are trying to find some solution to reduce the carbon footprint of concrete. So we all know probably that the carbon footprint of cement is around 0.9 kilogram of carbon dioxide per each kilogram of cement. But what if I told you that the biochar is a carbon negative material, which could of course sequester around 2.7 kilogram of carbon dioxide in each kilogram of this material. So this introduces material as a promising solution to reduce CO2 footprint of cementitious mixture. But of course, that's not the only aspect of the issue. We also have to take a look into if using biochar in our mixtures would help us satisfy the performance requirements. So here we are trying to use biochar as lightweight aggregate, and then we will try to see if this material as lightweight aggregate could act as an effective internal curing agent. The main research questions that are going to be answered in these presentations are: first, could biochar effectively keep internal relative humidity high and control autogenous shrinkage in low water to cement ratio systems? Also try to answer if biochar comply with ASTM C761 requirements, which is the ASTM standard for lightweight aggregates meant to be used as internal curing agent. We also see if grinding biochar particles and having a better distribution of them in cementitious matrix would help us benefit more from their internal curing capability. And we also want to see how using biochar as sand replacement as a lightweight aggregate would affect compressive strength, air content, and flowability. We also want to take a look at how cement hydration is affected in the presence of biochar as sand replacement. So this study will use biochar produced by two different manufacturers to enhance the general applicability of the findings. Those two manufacturers are called Metzler and American Biochar. Both of them use wood-based feedstock for their biochar production. Of course, the wood is different for two manufacturers, and I'm going to show you how these different feedstock will change the microstructure of biochar. But the pyrolysis temperature for both types of biochar are 700 degrees Celsius. The carbon content of Metzler company, the biochar produced by Metzler company, is a little bit higher compared to the American biochar. And here, just to make it clear, I'm going to point to the Metzler biochar, on-ground Metzler biochar as MET, on-ground American biochar as AB, and their ground forms as MET60 and AB15 respectively in my future slide. So, as I mentioned, we want to use both types of biochar in two forms, ground and on-ground form as sand replacement, see how they will affect our mixture's properties. So, of course, biochar particles has high CO2 sequestration capacity, but what else could make this material as a solution to a lightweight aggregate, to be used as lightweight aggregate in our mixtures? So this material is highly porous, and I'm going to show you the water absorption capacities in short, but you can see from the STM image taken from these materials in their on-ground form that it somehow resembles the feedstock, which was wood. And we could see that, especially in case of metal, we'll see that this kind of honeycomb structure, many like cavities, that could demonstrate this material as a material that could absorb a lot of water. And also the results showing regarding their oven dry relative apparent density demonstrate this material has a very lightweight nature. So compared to the normal weight sand that we mostly use in concrete, which has around relative density of 2.6, we will see that this material is much lighter. It has a relative density of 0.5 to 0.7. So first, I will start with using on-ground biochar. So to see if on-ground biochar could satisfy ASTM C7061 requirements, we characterize them in terms of particle size distribution in the first place. So we could see that both on-ground biochar, whose picture are shown on the right side, could satisfy the ASTM requirements for particle size distribution. But of course, MET is a little bit coarser, as can be seen in the picture. But the interesting fact about this material is that they have really high water absorption capacity. You can see that the water absorption capacity for Metzler is around 244%, and the ASTM requires us to only have around 5% of water absorption capacity. So imagine how much water this material could absorb, and that is mostly because of the porous structure I showed in the previous slide. For AB, it's a little bit lower. Of course, it was also obvious in the ASTM image that it has lower porosity. But another thing that ASTM requires us to take a look into is the desorption rate. So the desorption rate is how much of the water that you have absorbed could be released at a 94% RH. And we saw that Metzler biochar could satisfy that requirement, which ASTM says has to be 85%. The Metzler has a desorption rate of around 80. But the American biochar slightly fails to satisfy that requirement. However, because it still has like very high water absorption capacity, it will still probably be used as an effective internal curing agent in our mixture. The next step was to see if ground form of biochar could also be used as lightweight aggregate internal curing capabilities. So why ground forms can be used? Because you may wonder why ground something like powder as a sand replacement. So biochars in ground form, we did a mercury intrusion proximetry on them, and we saw that they're also really highly porous, even in the ground form. And also by grinding biochar particles, we probably have a better distribution of them in our cementitious mixtures. So that's why the incentive that we want to take a look if grinding biochar particles could enhance their internal curing capability. So we use ball milling method at a fixed ball to powder mass, and here's the particle size distribution of those ground biochar particles, and we measure the water absorption capacity and desorption rates as well. So for their water absorption capacity, there is no ASTM standard. What we do was we set the ASTM C7061 as a baseline for measuring the water absorption capacity of on-ground form, and then we deduct the cumulative intrusion volume of any pores which were larger than the D50 of ground form, and that's how we get those values. So we could still see that, of course, compared to the on-ground form, they had a little bit lower water absorption capacity because we are, of course, losing some pores, but their desorption rate is also lower. And that's because it's a little bit harder to draw water from smaller pores due to the enhanced capillary pores. Then, so when we characterize biochar in terms of gradation, desorption rates, and water absorption capacity, we wanted to see how much of biochar should be incorporated to mitigate autogenous shrinkage. So first off, we chose water seven ratio 0.36 because first off, ASTM says that if you want to take a look into low water seven ratio systems, you have to choose something below 0.4. And also, another thing is that we want to have the maximum degree of hydration, which is 100%. So if you go a little bit lower, let's say 0.35, we won't have that 100% hydration. So that's why we chose 0.36. And then based on the equation that you can see here that was proposed in ASTM, calculate the mass of lightweight aggregate, which is biochar in this case, both grounds and on-ground forms, to see how much biochar should be included to mitigate autogenous shrinkage. So for all of the ground and on-ground, all of the parameters showing that equation are the same, except that LWA, which is somehow an indicator of the desorption rate. So if you have a biochar with lower desorption rates, you have to include much more of it to get the same internal curing effect. So that's how mass of lightweight aggregate has been calculated. And then, with the goal of keeping the total volume of aggregates constant, we calculate how much normal weight sand has to be removed, and these are the replacement levels by volume of the biochar used in our mixture. So to see how biochar is affecting our cementitious materials properties, first it is a thermal calorimeter. So here is a graph showing normalized cumulative heat as a function of time. And as you can see, compared to the control mix, which has no biochar and as sand replacement, it was all normal weight sand, we could see that using on-ground met and AB at lightweight aggregate is enhancing cement hydration because we are getting more heat after 7 days. So this is showing that biochar is, of course, playing its role as an internal curing agent. We also want to take a look at compressive strength, air content, and flowability. So we measure compressive strength of our mortar mixtures at 1, 7, 28 days, and 90 days. And this is a graph showing the compressive strength for different mixtures studied in this study. So we could see that compared to the control mixture that has no biochar, and all of the mixtures that had biochar, you see a reduction in the strength. And that's why, why that's happening is because we are replacing sand with a porous material. Of course, we are getting benefit in terms of cement hydration. We saw that in the previous slide. But the negative effect of replacing sand with porous material, which is highly porous, dominates the compressive strength results. We also measure air content and flowability according to ASTM standard. So here's a table showing the flow number and air content for mixtures studied in this study, and at the same admixture content, I mean by admixture, superplasticizer and air-interning admixture, we saw that using biochar will reduce air content, which is attributable to the fact that biochar is mostly carbon, and carbon absorbs air. And we will also see that regarding flow number, more specifically in the case of on-ground biochar, we see a reduction, but in ground form, we could also see some improvement. And these biochars, keep in mind that were added in pre-soak state. So we pre-soak them in water 24 hours before the start of the mixing to make sure that their pores are filled with water so they don't absorb any water, because the water absorption capacity is exceptionally high. So we want to make sure they don't absorb any water that was meant to react with cement. So in order to evaluate if these materials are effective internal curing agents, we also did internal relative humidity measurements. So we built up a setup, and you can see that we seal it properly to make sure there is no loss of moisture from any external sources, and anything that is happening is within this. It's because of the reaction of cement and water. And what we get out of this, here you can see a graph showing the internal relative humidity as a function of age. And compared to the control mix, which again has no biochar, and it was all normal weight sand, we could see that using more specifically on-ground biochar would help us keep internal relative humidity high. In case of using American biochar as lightweight aggregate, we could see that even after 60 days, we are keeping IRH as high as 99%. And also we could see here that using ground form of biochar will somehow adversely affect the internal curing capabilities of biochar, because probably it's harder for those smaller particles to, for cementitious mixture to draw water from those smaller. Also, we want to see how autogenous shrinkage is affected in the presence of biochar as lightweight aggregate. So we measure autogenous shrinkage according to ASTM C1698. And what we get out of it is totally in compliance with internal relative humidity result. So here's the graph showing the autogenous strain as a function of time. And we could see that compared to the control mix, which has, again, no biochar, we will see even some expansion in the mixtures that has biochar as lightweight aggregate, specifically those that were used in on-ground form. But again, comparing ground and on-ground form, we will see that grinding biochar particles is adversely affecting their capability to control autogenous. So to wrap up, the main conclusions that were get based on this study was that biochar particles could effectively keep internal relative humidity high and control autogenous shrinkage in low water cement ratio systems. And we saw that on-ground met biochar particles completely satisfy ASTM C7061 requirements, while using AB would result in failing only the absorption requirement. We saw that grinding biochar particles is not only time-consuming, energy-consuming, and costly, but also would adversely affect their internal curing capabilities. And we see that even though biochar particles could enhance cement hydration due to internal curing, the negative effect of increased overall porosity will result in a lower compressive strength in their presence. And finally, we saw that if there are added increases, we will see some reduction in air content. So we'll probably have to add more air entering atmosphere demand to get the same air content. Thank you so much for your time and attention, and I will be happy to answer any questions.